Okay. Well, thank you, everybody. It's really a pleasure being with you, and uh, I'm very grateful for Sabrina for inviting me. I'm really honored. Um, what I've tried to do in this lecture is really give you a survey of the area of fatigue. It is a multidisciplinary area. It includes material science, solid mechanics, dynamics, signal processing, and so on and so forth. So in this lecture, it's just going to be a taste of various fields, and I'm not going to be able to cover everything, but I'll just give you a flavor of some of the topics that hopefully you'll be exposed to this morning and this afternoon. So I'll give you a quick history of fatigue, and then we'll look at the behavior of the materials, the progression of fatigue, and applying various methods to estimate the life. And I give a few examples to demonstrate those concepts. And in a very simplistic way, the way to think about fatigue is really just like human, just being tired. And I really like this quote by Rusty Gray, who said, materials are a lot like people. Imperfections control their behavior. So as we age, our knees get tired or our hips get tired. They get fatigued. Um, they wear out, and that affects our movement. So in your 20s, you run fast. In your 50s, 60s, you run slower. In your 70s, you can't run anymore. Maybe you just walk. So that's really the idea. And I give an example here of hip replacement. And believe it or not, the expected life of hip replacement is about 10 to 15 years. And then they have to go in and replace those the hip, the artificial hip. And I believe you have only two that can operate on you twice to replace your hip. So the second time or the second hip that you get, they will not replace it. So it's really interesting that the science of fatigue, if you will, it's really an old science. It's been around for more than 150 years, and even today we still struggle with fatigue and trying to understand fatigue. And part of it because we're always coming up with new materials, more complex engineering designs, harsh environmental conditions, and we have to go back and reevaluate how we approach these problems and solve them. So in a nutshell, the fatigue is really the process of damage and failure due to a cyclical stress or cyclic stress, some folks call it. Uh, and this repetitive stress causes the gradual deterioration of the material. And initially, you can't really absorb that fatigue in the material with a naked eye, and it just built over time. Uh, as far as we know, in terms of really looking at fatigue from an engineering and design perspective, is disasters really related to bridges, but also to trains and railroads. And that's because of economics. Folks, especially in Europe, focus very heavily on trying to understand uh, the process of fatigue. There were tests. One of the first that we know of, an engineer or designer by the name of Albert. I believe he's from Germany in 1828. He looked at fatigue in mine host chain. Uh, the word fatigue itself, we can trace it back all the way to maybe 1839 in a textbook called Mechanics by a French engineer. And then really, these disasters kept on being more aggressive because the engines on those trains were stronger, so the fatigue or the stresses induced on parts in the train were also aggressive as a result. And one of the godfathers of fatigue, and you'll see this in a lot of textbooks, is August Forel. He actually one of the first to really standardize material testing for fatigue and trying to understand fatigue. Fatigue failure and designing for fatigue evolved over the years, and it became part of our engineering process. We developed the theory, the processing, the characterization, and it is really now an integral part of our engineering education, especially if you are in the mechanics side of engineering. In terms of the economics, it has really huge impact. I'm not really sure about the impact in Europe, but I can tell you in the US, it's about 3% of our gross national product, which is extremely expensive. I'm here showing here some really very disastrous accidents due to fatigue in offshore rigs, aircraft, especially military aircraft. They experience significant stress loads. With that, we have to inspect these infrastructure, high value infrastructure on a regular basis because we want to prevent fatigue. Again, it's very expensive to investigate and to inspect fatigue. And that's why we really need to understand it and understand how to design to mitigate fatigue and prevent fatigue or slow it down. So fatigue has 3 stages. The first stage is the initiation of fatigue. And let me see if you can see my, no, you can't. Oh yeah. So the initiation process, and then the propagation. And the propagation process, you'll see after the material completely fractures, you see the wave effect. And that kind of a graceful, slow damage. And then in stage 3 is the fracture, which is a catastrophic failure and a sudden failure most of the time. So I show here a couple of samples of this wave effect. You've seen this in the previous slide, how the damage originated here. And this is where we call it incubation or initiation of the crack, the wave propagation, and then when it's overload and the sudden or the complete rupture. Now the wave shapes, it differs from one material to another. So the wave shapes in this steel 4340, the waves look different than the waves in the 18 magnesium steel. Now the initiation could be, there are several mechanisms for the initiation. I just show here 3. One is the slip band, where you see extrusion and protrusion of the material at the surface, and that causes the initiation of the damage. Sometimes it can be an inclusion or imperfection in the material, or it could be due to grain boundary effect. And then as a result, the damage grow, and then it becomes more of a stress concentration, and the separation in the material increases as we increase the load. And here I show some of the various plastic blunting mechanisms. Of course, for polymer, it's a completely different story than metals. I've showed you the incubation or the initiation, the wave propagation effect, and then the complete fracture or rupture. Here, it's more like a fibral break in the material that looks almost like you're breaking a bunch of fibers. And you'll see that also, especially in composite materials, because they don't consist of grains, they consist of fibers. So you're breaking the matrix and then the individual fibers as the fatigue propagates. In terms of analyzing against fatigue or reducing the progression of fatigue, in general, there are three approaches: stress-based, strain-based, and the fracture mechanics-based. In this lecture, I'm going to cover the stress-based and the strain-based. And I'm hoping that in the next lectures, they'll cover the fracture mechanics aspect of it. So if you think of a cyclical load, maybe we can think of a sine load or loading condition. This is the time history. And when you look at the magnitude, we want to know the maximum, we want to know the minimum. So in this particular one there, this is a constant amplitude loading. And we want to also know the range. In some textbooks, they call this delta sigma. I call it delta range for the R stands for range. And we want to know the mean. And we'll see why we need the mean very shortly. Did I miss anything here? I think we covered everything here. Okay. So in terms of the stress range, it's really simple. You got maximum, you got minimum. It's just the difference between the two. In terms of the amplitude, if we want to, if you want to calculate the amplitude and your mean is not zero, it's not really just half the maximum and the minimum. You have to take into account if the mean is positive or negative. And it's this simple calculation here, where it's the maximum minus the minimum. And here it's just the addition of the 2 divided by 2 to calculate the mean stress. Now, we have to be careful when we look at stress life diagrams. Some refer to the life as a cycle, and a cycle is really a full cycle. But in some textbooks or standards, they refer to life as reversal. So each cycle has 2 reversals. So just keep that in mind. Okay, so a couple of more important parameters to keep in mind is the stress ratio. And the reason we want to know the stress ratio is tell us a little bit about the resilience of the material. So it's the minimum divided by the maximum. So Increase in the R really means that you decrease in the crack initiation life. The amplitude ratio is nothing more than the amplitude divided by the mean. Okay, just another way of looking at or quantifying the load in terms of ratios. And then we talked a little bit about the frequency briefly here. So like I said, this is just one cycle. And you'll see in terms of the frequency, whether it's in hertz or radian per seconds. Again, keep that in mind. So if you have a gear rotating 600 rotation per minute, means that the frequency is 10 hertz, right? So you got 600 revolutions divided by 60 seconds, and that gives you the 10 hertz. So we talked about the, I mentioned briefly the reversed cycling. So if it's completely reversed cycling, it means that your mean is 0 and your stress ratio is -1. If you have compression, so when you load in cyclically, in some instances you'll be in pure tension. In some instances you may have some compression. So if you have compression tension cycling, now you can't say that the mean is 0, and you have to consider that shift in your calculation and your assessment of fatigue. And then we have what we call 0 to tension cycling, meaning that the part is completely under tension loading. Now, when we calculate the stress for fatigue, we want to differentiate between point stress and nominal stress. So for something that's under tension, like this sample here, the point stress and the nominal stress, or your average stress, cross the section area, it's going to be the same. Okay. If you are under elastic bending condition, your point stress is not going to be the same as your nominal stress. Okay, so we need to understand the loading condition of the part. If your part has a hole in it or has some feature in it, again, your point stress here is going to differ than your average stress or stresses across the section area. Okay, and I show the formula here to calculate the stress. In this case, when you have a hole or some feature, we need to go back to the standard books and find the concentration factor, or stress concentration factor, and multiply the nominal stress by the concentration factor to get our sigma stress. Okay. Here I show an example of calculating the von Mises stresses when you have a cyclic or cyclical loading stress. Here I show if you have a XY stresses, and the has the sine component in it here as well. So if you were to calculate the von Mises stresses, we know how to calculate this. You got sigma x squared. This is wrong, by the way. Please fix this in your notes. This is supposed to be y. Sigma y squared minus sigma x sigma y. You plug in your y's, your your sigma x's into this equation, and now you have your von Mises with respect to the sigma y. And I plugged all of it in here. If I have let's see here. Yeah, if I have my y equal to 0, then my amplitude is equal to beta. All right, so to plot the, what we're really after is knowing the stresses versus the number of cycles. And that the number of cycles is what we call fatigue. And for that, we need to know the stress amplitude. Let's say we calculate the stress amplitude and we trace the number of cycles. And we know that for each stress, there is a number of cycles associated to failure. The issue here, if you plot them on a conventional scale here, it's really difficult to read these numbers here. And that's why we need the log scale for the number of cycles. If we do the log scale for the number of cycles, it will stretch out, or we'll move this, and stretch it out, and then it makes it really easier to read those stresses. Okay. And the calculation is really simple. You've seen this in your math courses. It's really not other than a constant plus another constant times the log of the number of cycles. And from that, you can express it in a power form. And this becomes important because this B here becomes a material constant that you can actually look up in standard books and materials handbooks. And that brings us to what we call the stress-based approach. And that works for elastic behavior. I need to keep an eye on the time. Let's see. So we have another maybe 20 minutes, so I'll try to hurry up. This is the Baskin law, which is really it's your range stress, which it can be expressed as an elastic strain times your elastic modulus, and from that we can substitute the stress that we calculated in the previous slide in this power form. And if we do that and substitute the stress in terms of the express it in terms of the strain, as you see it here, then we end up with this formula here, which is the Baskin law. Okay, and again, this works for elastic loading conditions. Okay. Here I show an example of a steel specimen, and you see the curve going down, and then it plateau at a certain stress. And they call this the endurance limit. However, I would caution you against really using the endurance limit. Personally, I try to avoid it because to me, there is no such thing as endurance limit. So you'll see in textbooks that the endurance limit is as long as you're below this loading condition, you will never fatigue. Well, that's true if you have a pristine sample, well polished, It doesn't have any defects. It doesn't have any manufacturing issues. It was machined perfectly, and that's almost impossible in manufacturing. So I would be very, very careful when I use that, when you use the endurance limit. Okay? And the reason why, I caution you against this, if you look at a military helicopter, for example, it goes through really aggressive maneuvers. You see some landing conditions when they land these helicopters, especially in the battlefield. They land them really hard. I mean, they drop them. They want to get rid of the soldiers, put them back in, and take off. Sometimes they go through storms. They have to land again somewhere. So you can see that the amplitudes of the cycles will vary. Okay, so keep that in mind. In terms of the testing, we talked a little bit about World, who really standardized this process. And here we show how you can load a specimen here and be able to apply a load to simulate a search and loading condition. And this example here, you have a shaft with a motor and you have a weight on top of it here. So it gives you the bending and compression and tension simultaneously. If you want to look at materials in terms of the meso microscale, there's a method called a dynamic material analysis, where you load a very small specimens in an apparatus like this one here. And this here is a thermal chamber. So you can load it in compression or tension and expose the material to thermal cycling as well too. Testing could get even more sophisticated than that. You can look and monitor the material at the macro scale with laser vibrometer while it's fatiguing, either rotation here in an engine or in simulated helicopter blade on top of a shaker. So you're simulating the rotation as well as the axial loading. Right. You can also look at it in a meso microscale and do the interruptive testing, analyze your sample, go back, fatigue it some more, and then bring it back to the lab. Or in some instances, you can do the characterization in situ while you're testing using non-destructive evaluation or structural health monitoring. Again, I mentioned that there will be some variation in the material quality. There will be some defects. There will be some impurities, some surface imperfections. And because of that, you'll see a variation even within each stress point. So think of each stress point that you see on the SN curve as a mean of a probability distribution. And for each point that you see here, it has its own probability distribution curve that associated with it. Okay, and that makes it even more challenging. So now you have to bring in statistics and probability into this process. And to give you an example here of a aluminum 7075, this is high-grade aerospace aluminum 7075, and you can see the variation is really astonishing. For example, here, taken from NASA handbook, here they have a failure around, let's say, about 40,000 cycles, right? And then same, it came from the same lot, right? And then here, they have another point around 200,000 cycles. So what do you do when you have a variation in the material like this? Okay, it becomes really difficult. So to deal with this kind of variation, the mean stress effect, there are various techniques that can be employed. Here I show another example where you have a bunch of ascent curves, right, for different means. Now we're talking about the mean, not the mean in the distribution of the samples, but the mean in terms of the amplitude, minimum to maximum, right? That also has an effect on the life of the sample. So you have to keep that in mind as well too. If your mean is 0, your curve is going to be different than a mean of 400 megapascal. Okay. Well, the best we can do right now in terms of design, using the Goodman equation, which is really more or less of a curve fit. And then there is another method called the Gerber parabola. There are several methods out there. You just have to choose whatever fits your data the best, really. There is no way around it. There are, of course, far more advanced techniques that I think Sabrina will cover, or her colleagues will cover this morning. Okay. Now, again, those techniques I'm showing you right now is think of them as zero order or first order in the design process. And then after that, you need to really get into high fidelity modeling and simulation and analysis. Okay. Going back to how to apply one of those techniques, this is the Goodman method that I use here for a steel part, where I'm trying to calculate a safety factor based on a yield stress that I know of, and based on my critical stress and my mean stress. We know I covered how we calculate the mean and the amplitude. And now I have a relationship between the amplitude and the mean based on the fluctuation and the load. And then I plug all of this into the Goodman equation. And I get a critical mean stress and I get a critical amplitude stress. So this is the critical mean, critical, I'm sorry, this is the critical amplitude, critical mean, okay? And then I pick one that's the lowest, and based on the lowest one, I calculate the stress factor because I'm trying to be conservative, and I divide it by my mean of 20. And that tells me that my safety factor is 2. Okay. Okay, we talked about the effect of the variation in the mean. Now, if there is some kind of a hole or some kind of feature in the like an opening for an O-ring in the material, that will also shift its stress ascent curve rather. Okay. Now, the environmental condition is also critical. So if the component is operating in outside in the air, exposed to the atmospheric environment, it's going to have higher ascent curve than a component that's operating in under seawater or some kind of water that has salt in it, or maybe in an environment by the shore where it's exposed to humid environment that contains salt water. Other effect is, we talked about the air here. Oh, yes, the pressure and the cycles. So if the frequency is low versus a frequency high, under high frequency, your part will fail much faster. And same thing here, if your temperature, if you operate in, I apologize about the Fahrenheit, this is what we use in the US, Fahrenheit. So if you operate under 1300 Fahrenheit versus 1500 Fahrenheit, 1500 Fahrenheit is going to fail faster than a 1300 Fahrenheit. Okay. All right, so now we move to we talked about the stress approach. It's appropriate for elastic, but now if you have high plasticity, it's no longer valid. You have to use, you have to include plasticity into the analysis, and that takes us to Kaufmann relationship. And for the sake of time, I'll just show it to you here and jump into the derivation in terms of the approach. Here, the strain is basically now elastic, which is the stress base, and the plastic, where we include the plasticity into it. And we include now the Kaufmann into this equation. And now we have both components included in the calculation. And ultimately, what I want to do, I want to calculate the strain. And this, if you go through the math, you end up with this relationship here, which includes the elastic behavior and the plastic behavior, okay? And here I include an example. It's really straightforward. I give you the material properties, the constants, and all you have to do is just plug into this equation and calculate your strain. Okay. We covered this, and the reason I bring it back because I want to remind you of the cumulative effect. So the sequence of the stress, not just the amplitude, is also critical and affects the life. And for that, we need to include each environment, or each sequence rather, into our calculation. So let's say this is one environment here and one. Now the stresses here are lower. This is another environment and then another environment here. And we add them up in terms of ratio and make, if we equate this to one. And this is called the minor rule. Okay. This is similar to the minor rule, that we multiply here by a constant. I included the reference at the end. Go through it. But basically, what it is really including a repetition. So if you have a one environment here, but those two environments are repetitive, then we can calculate it using this equation. Okay. Now, in terms of the design, this is just very basic, and I included a reference here. This is bad design when you have sharp angles. So to overcome that, you introduce a fillet radius, some kind of cutouts, Same thing with holes. You enlarge this area here around the hole because you want to provide a stress relief. So that's in a nutshell what I was hoping to cover in this lecture. I think I nailed it. I think we're 45 minutes. So let me know if you have any questions.
Okay, Ed.
Yeah.
Thank you for your talk.
My pleasure.
Yeah. Any question or comments from the audience? Can you hear me?
Yes.
Any question or comments?
No, no.
Okay.
Ed, would you like to say some words about the position that are at your university?
Yeah, briefly, if you don't mind.
Did you prepare? Okay.
Yeah, so I have a couple of slides here on the open position. So I have two positions. One is a postdoc, and the other one is a PhD. And what we're looking for here is someone who's really enthusiastic, passionate about research and multidisciplinary research. It's about architecture materials where we embed living cells and bacteria into the structure to get us functions that you can't get in conventional structures, such as self-healing and sensing within the structure, but also maybe they can act also as muscles into these structures for robotic applications and aerospace application. The position is in the limited lab, and that's in the aerospace or the aeronautics and astronautics department at University of Washington. It is, I believe, the first aerospace department in the U.S., and it's in the city of Seattle. Really beautiful city, awesome city. A lot of outdoors activities and awesome city life. And in terms of the research, we'll be, in terms of application, we'll be studying and looking at emulating diving birds and taking some actuation from those diving birds into these architecture structures, but also borrow some of the muscle behavior, soft tissues and soft actuators from nature to emulate motion such as worm and snakes. And if you're interested, I got my email there in the bottom. The position starts in about 1 year, September 2021.